Okay, so in this last video for this week, we're going to be looking at the reactions of the acyl chlorides, and we're going to have a look at an extension exam question right at the end. The reactions of the acyl chlorides are relatively straightforward. As I reminded you in the end of the last video, the chloro is a very good leaving group, so they all react by losing the chloro and gaining another group. So this is all substitution reactions. Okay, so as we've said, this is our acyl chloride functional group, and it is a highly reactive functional group. In fact, it reacts rather than dissolves in water. So the reaction conditions for all of this are dry, because they will react with water. So we want them in what we call an anhydrous conditions. Otherwise, we'll just get them reacting with any water that is present. Okay, so the first reaction we're going to do is ethanol chloride and actually water. And again, as we said, the conditions are dry and we just need room temperature. This reaction happens very quickly and very exothermically. So we're going to have our water molecule here, and that lone pair on the oxygen is going to attack that delta positive carbon, and eventually it's going to eliminate that chloro group there. So we get as our product, we've got our C, double bond stays put, the chloro has been lost, so there's a wiggly line there, as has one of the hydrogens from the water, and we've got these bits joined together. So I've got an O and an H, and I've obviously got HCl as my other product. So the name of the product is ethanoic acid, and I've made a carboxylic acid. So the homology series we make is a carboxylic acid. So we can turn a carboxylic acid into an acyl chloride by adding PCl5. If we then took the acyl chloride and got it wet, it would turn back into the carboxylic acid. Okay, so the next one is our acyl chloride with ethanol and alcohol, and in this case we're going to make an ester. So there are good and bad reasons for doing it this way. A good reason is it is non-reversible, so you get a much higher yield. However, you do produce HCl gas, which is corrosive. So it's got good and bad points. It's a non-reversible reaction, so you're going to get a higher yield, but you are producing a lot of HCl gas, which is acidic, and that's quite a dangerous gas. So again, we're going to do these in dry conditions. All the conditions are the same, they're all dry and room temperature. So I'm going to take my acyl chloride and I'm going to add some ethanol to it. And it's a very similar reaction to the last one. I always make HCl as one of my products. So I've got HCl coming off because I'm going to get, that's my leaving group, and then I'm going to lose this hydrogen. I've got to have a very delta positive hydrogen that I can lose. So that's going to make my HCl, and then my other product is what we call an ester. So a double bond oxygen coming off, and I've got that O coming from my alcohol, and that's joined onto my C, and I've got an H, H, C, H, 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 and basically I've made an ester. This is called ethyl ethanoate. Ethyl ethanoate. Okay, so the last two reactions are with concentrated ammonia and with a compound called an amine. So again, we've got dry conditions, room temperature. I'm adding ammonia this time. And again, same idea. I'm going to lose that chloro group. I'm going to lose one of the hydrogens that is attached to the nitrogen. So I'm going to make my HCl. And where I've lost them, that's where I'm going to join my molecule back together again. So I've still got my CH3, C, double bond O. This time it's joined onto this nitrogen here where I've lost the hydrogen from, and I've got two other hydrogens joined onto that. This is what we call an amide. It's an amide functional group. I've got 2 carbons, so it's ethanamide. Ethanamide. The next reaction is with the acyl chloride again and an amine, ethylamine in this case. Don't worry a bit too much about these functional groups because we're going to study them later on. But again, dry conditions, and my amine, it acts a lot like ammonia. So you've got nitrogen, we've got a hydrogen, and then I've just got a C2H5 group on it. So you can think of it like ammonia, where one of the hydrogens has been replaced with an R group. So again, we're going to lose a hydrogen, going to lose the chloro. Where we've lost groups, that's where they're going to join together. So I've got my HCl, and I've now got, again, same thing, double bond oxygen, again joining through the nitrogen, but this time the nitrogen has an R group on it, a C2H5 group. And what we've made is what we call an N-substituted amide. It's N-substituted because I've got to substitute on the nitrogen rather than on the carbon. So this product name would be an N, and this is an ethyl, N-ethyl, and then I've got 2 carbons here, ethanamide. N-ethyl, ethanamide. Okay, so this is a bit of extension work. This is the mechanism for this reaction. The first step, it's very similar to our mechanism you've seen before in the nucleophilic addition mechanism with the carbonyl compounds. So we've got this lone pair on our oxygen here attacking this very positive carbon here, and this is pushing the pi-bonded electrons out from the pi bond onto the oxygen. This next step is a little bit more complex. So you've got this this group here, this oxygen joined onto the carbon. This oxygen has gained a positive charge, and this oxygen has gained a negative charge. And then we have this kind of internal rearrangement of our electrons going on. So the lone pair on this oxygen reforms this double bond. The chloro electrons come out to release the chlorine. Remember we said the chlorine is a very good leaving group. And the pair of electrons here between the oxygen and the hydrogen go back to get rid of the hydrogen and to get rid of that positive charge there. So it's quite a complex mechanism. It is extension. It's not one you're expected to know, but it does help us answer the next very nasty exam question. Okay, so this was a particularly nasty exam question which was asked in 2017 on the paper 3. Very few people actually managed to get all 3 marks for it. It was a particularly nasty one because it was asking you to predict a mechanism based on what you knew about the nucleophilic addition mechanisms of the carbonyls. But I am going to go through it. So it's asking you to predict the mechanism for the reaction between the acyl chloride and ammonia. So we've got our acyl chloride, which is what we're starting with. So I've got my CH2 group and my CH3 group. Just going to get those out of the way there. I've got my double bond oxygen and my Cl, and I have my ammonia molecule, which is what's coming in. So I've got the lone pair on that nitrogen. I've got delta negatives on both those and a big delta positive on that carbon. So I've got the lone pair coming in there. And just as you do in nucleophilic addition mechanisms with carbonyls, that pushes the pi-bonded electrons out and on to that oxygen. So we get this rather weird looking intermediate. So again, I'm just going to keep those CH3, CH2 groups out of the way. So I've now got an oxygen with a negative on it. I've got my chloro, and I've brought my ammonia, and that is now added on. Now, there's a slight problem in that this nitrogen's lent its lone pair to the carbon, which has meant that it's now got a positive charge on it. Both of the electrons have gone and sat onto the oxygen, so the oxygen now has negative charge. So now what we get is a kind of rearrangement of all of our electrons. That lone pair there is going to come back in to form that double bond. That's going to push out that chloro group, and one of those hydrogens attached to the nitrogen is then going to go back and get rid of that positive charge. So we're going to have that all internal arrangement. I said it was quite a complicated little thing. But then we finally get our product, because this lone pair coming back in here has formed this carbon-oxygen bond. You've lost one of your hydrogens, and we're just going to leave the rest of the molecule as it was. So I've got my CH2 and my CH3 group, and we've got chloro group there. You should be able to get that first step. It's this internal rearrangement that's going to cause the issues, but it's just worthwhile having a think about it, having a look at it. As I said, it was a particularly nasty question. Very, very few people got this right. Okay, sorry, I should have a hydrogen there as well. Okay, so that finishes off this section of the notes looking at acyl chlorides, and that actually finishes off the notes for this week. So next week we're going to be looking at the esters, and we're going to be finishing off this pack for uploading on Friday. So until then, take care, stay safe, speak to you soon. Bye bye.